Hey everybody, Dr. P here. I'm getting kind of pissed off because I've been trying to compute this triple integral for the last few minutes. I've tried two different things so far, and neither one of them has worked. So I'm going to try a third thing now, and really hope that this one works because I'm getting kind of tired of trying different things. Uh, when I started doing cylindrical coordinates earlier, I made a choice where I decided to put z on the inside integral and r on the outside integral, or the middle one, I guess. I'm going to try switching the order of those two and see if that helps at all, because I knew that when I set up that integral, I really wanted to integrate with respect to r, and instead I was stuck integrating with respect to z. If I could just arrange things so I integrate with respect to r first, I feel like that might help. So I'm going to try that and see if that gets me somewhere. So this is in cylindrical coordinates part 2. So again, I'm going to have 3 integrals. I'm going to hope I can still put theta on the outside just because I'm really used to doing things that way. And theta is going from 0 to 2 pi regardless. I don't think that moving that around is going to help anything. But this time I'm going to try z here and r here. So my function is going to be delta equals square root of r squared plus z squared. That's not changing because I'm still in cylindrical coordinates, times r dr dz d theta, which is basically the reverse of what I tried last time. So this time, let's see if we can figure out what z is doing first. Z appears to be going from 0 to 2. Those are the possible values of z. So I think that's fine. Again, I can't just have r going from 0 to 2 regardless of z, because that would give me a cylinder. So I need r to do something specific depending on what z is. Well, if z is 2, I know that r, the radius from the z-axis, goes from 0 to 2. That's good. When z is 0, r goes from 0 to pretty much nowhere. R goes from 0 to 0. And if I'm halfway, if z is equal to 1, then I think my radius is going to go from 0 to 1. So I feel like it's a pretty good guess that r is going from 0 to whatever z is. Now that's interesting. By the way, there is a way to check this. You don't have to just go in and do geometric reasoning until your eyes bleed. You can actually figure it out based on what's inner in this solid and what's outer. The inner radius is always 0 because no matter where I am, I'm always integrating starting from the z-axis. But the outside of this solid is determined by that cone, and that cone is given by the equation z equals r. So what I'm really doing in my head is I'm flipping this and saying this is the same as saying that r equals z. R is going to go to whatever z is. Okay, so you can still use that algebraic approach even if you're integrating in a way that you're not usually comfortable with. Okay, so now I have this integral set up. I feel pretty confident that this is accurately describing the solid and the function I'm integrating, and of course the volume element. Still got that extra r there. So let's see if this works. Let's see if we can actually integrate this. I'm integrating with respect to r first, so I'm going to try my usual trick of letting u equal r squared and du equal 2r dr. So what I have here is r squared plus z squared, quantity to the 1/2. Actually, to make things simpler, I could let u equal r squared plus z squared. I think that's a little bit more straightforward. And then this is still true because z is a constant. It's different. Its derivative is not going to matter here. So theta still from 0 to 2 pi. Z still from 0 to z equals 2. And then r still from 0 to z. But now I'm going to rewrite this as u to the 1/2 times 1/2 du, and then dz d theta. I know I'm using my u's and my r's a little loosely here. Some of your instructors tell you that you should suppress limits of integration on this if you're going to do something like this, like use a u substitution here. I'm not going to worry too much about that. I'm going to restore everything to r at the end, so I'm not doing anything fishy here. Still got theta going from 0 to 2 pi. Still got z going from 0 to 2. I think now I'm ready to go ahead and try integrating this. This is u to the 1/2, so its integral is going to involve a u to the 3/2 somehow, but I also need to multiply by the reciprocal of 3/2, which is 2/3. So I think what I'm going to have here is 1/3 u to the 3/2 evaluated at 0 and z, and then integrated with respect to z and theta. Now, just to save myself a couple of steps on the board, I'm going to go ahead and replace u back without changing much of what I've done here. So still from 0 to z. But now this is going to read 1/3 times, and what was it? It was r squared, u was r squared plus z squared, quantity to the 3/2. Okay, this is already starting to look a little ugly, but I think I'm going to persist with this and see if I can make it go somewhere, because I put a lot of investment into this, and I really don't feel like starting over. All right, so I've got r. Remember, these are values of r, and this is where it's really useful to put these in, because this reminds me to substitute for r, not z, which is a little bit tricky. Okay, now I have r going from 0 to z, which means now I really have to get rid of some of this. So I've got integral from theta equals 0 to theta equals 2 pi of integral of z equals 0 to z equals 2 of, and let's see, at z, this is going to come out to 1/3 times 2z squared to 3/2 minus, and then at 0, this is 1/3 z squared to the 3/2 with respect to dz d theta. Now that's interesting. That's a lot cleaner than what I had before. I don't have square roots of sums anymore, which I kind of like. And in fact, because z is always positive in this problem, I don't have to worry about issues that might occur if I take something squared to the 3/2, like needing absolute values and stuff. This is just going to be 1/3 times z cubed, I think. So I've got integral from theta equals 0 to 2 pi. Don't worry, we'll get to the point where we figure out what to do with theta in just a bit. Z equals 0 to 2. And then here, if I just do some algebra, I think I find that I can factor out the 1/3 first of all. And I can distribute this power over the product. I get 2 to the 3/2 times z cubed minus z cubed. I've already factored out the 1/3 dz d theta. And in fact, with a little bit more work, I can get this down to something even simpler. As a matter of fact, no, let's go ahead and wait. Let's go ahead and do this first. Z equals 0 to z equals 2. And I've got 1/3. And then factoring out the z cubed, I actually get this funny constant term here. I got 2 to the 3/2, which is 2√2, minus 1 z cubed dz d theta. And this part now is a constant that can be pulled out of the integral. Now 1/3, 2√2 minus 1, integral from theta equals 0 to 2 pi, from z equals 0 to z equals 2, z cubed dz d theta. Now this is a lot simpler. I know how to integrate z cubed with respect to z. That one's easy. That's 1/4 z to the 4th. Putting in some missing equal signs there. 1/3, 2√2 minus 1, integral from 0 to 2 pi of 1/4 z to the 4th from z equals 0 to z equals 2. I'll just put the limits in there. 0 to 2 d theta. This is going to come out to 0 when z equals 0, and at 2 this comes out to 4. So I think I'm going to have something fairly nice here. So this is going to give me 1/3, 2√2 minus 1, integral 0 to 2 pi of basically 4 d theta. Well, the integral of 4 d theta from 0 to 2 pi is just 4 times this range here, 2 pi. So I'm going to have 8 pi, 4 times 2 pi, 8 pi over 3, 2 root 2 minus 1, which of course was my first guess when I set up the problem. Anyway, that was interesting. That worked out, depending on your definition of working out. It took quite a bit of work to do, and it used some U substitution and some other, and mostly just a lot of persistence, really. I mean, I didn't have to do anything fancier than U substitution here, but it took a while, and it took setting up the cylindrical integral the right way. That was a lot of effort to get an answer that ugly. But now that I'm here, I'm kind of wondering, would it have been easier to evaluate this integral if I had set it up in spherical coordinates? So in the next video, I'm going to show what happens when you do that. Stay tuned.